So at this point in the show, I'm assuming everyone has heard about this thing called explained data, or at least many of you showed up to a talk about explained data. The idea of explained data is to go from what's going on in your data to helping helping a user understand why something is happening, helping them explore it. My colleague Bethany Lyons was using explained data the other day, was working on putting together a demonstration, working on putting together a talk for here, and she happens to be based in London, but was working on data about consumer spending in the United States and trying to explain different things by state. And she'd started sort of probing into Utah, and this raised a lot of questions about where these numbers were really coming from, what was really saying. She got a little bit confused. Those of us who were more familiar with the United States started cautioning her to be very careful in what she was trying to explain or what conclusions she was trying to draw. And she really wanted to get a better handle on sort of quantitatively exactly what's going on behind explained data. And so that's why we put this talk together. We want to make sure that people have an understanding of what's happening behind the scenes so that when it's potentially delivering confusing results or someone comes to you asking for more detail or why did it say that or why didn't it say that, you might be in a position to start to answer that. So I'm Richard Tibbetts. I was the CEO at Empirical Systems, a company that Tableau acquired back in June. Empirical Engine became the foundation for explained data. And I'm joined today by Rachel Kelmar, who's the product manager for explained data. We're going to talk to you about a couple of different things. I'm going to give you a little bit on where explained data came from and the analyst level, industry analyst, the very high level notion of how explained data works, what I tell people in a sales situation about how explained data works. And then Rachel's going to come up and give you details about what's really going under the hood and what you can do about it. We're both going to run off to catch a flight immediately after this talk, so we'll have some time for questions. But you should also feel free to email us, follow up in any way, in any way that makes sense. So where did explained data come from? That's an interesting question. So we built this company called Empirical Systems. Empirical came out of a research lab at MIT. There was this project called BayesDB. BayesDB was part of the Explainable AI initiative from DARPA. So we were trying to figure out how do we make data science, machine learning types of things accessible to domain experts who need to understand why they're making certain decisions. And there are a couple of different technological approaches to that. There were some earlier talks, which I imagine you can get recordings of, about explainable AI more specifically. But the approach that the BayesDB project took there was to build a system that would automate the kind of analysis that a trained statistician would do, and then allow you to query that interactively. So the big idea was rather than generating a report that explains what the model is doing, we're going to allow people to ask lots of interactive questions and sort of follow-ups, much the way you would quiz a human expert if you wanted to understand why they were making their decisions. And so we commercialized that software, brought it out into a company called Empirical, built a whole new engine with a different set of underlying algorithms and a somewhat different approach, and really started to tailor it towards analyzing business data. And again, continuing to deliver on that interactive performance for being able to ask and answer many different questions. So then we got into this, a number of conversations with partners, we built it out industrially, and we started talking to people who wanted to buy the company. And what we found was that everybody who wanted to buy Empirical had the same question, why are sales down? That they were sure, so basically having surveyed every BI vendor in the space, more or less, this was the question people wanted to answer. Amusingly, it's not a question that Empirical knew how to answer before we got here. You can think of Empirical as an engine for automating small bits of statistical analysis, much the way a database automates writing little queries and answering sort of summary statistics about data. And so the Empirical engine is able to do many things, but you often have to put together sort of multiple queries or multiple analyses in order to get to a particular answer. And when we started talking to people about this why are sales down, one of the things we found, especially after we arrived at Tableau, is that the Empirical engine did not understand aggregation at all. In fact, the vast majority of data science tooling has no idea what's going on with aggregation. You get to your sort of population of interest detail level, and that's where all your statistical analysis occurs. Whereas one of the things that's going on in most sort of business analytics and things like Tableau is that there's a lot of aggregation. So what does it mean to answer the question, why are sales down? Well, you don't want to know what's driving sales in general. The answer is number of salespeople, price, discount. You know, it's easy to identify, or rather you can build software to identify the sort of normal drivers of something. But that doesn't answer the question people usually have. They want to understand why sales are down like today. And they also don't want to understand what's the biggest component of sales having changed. Because if you ask why Tipico sales are down, the answer is financial services, because that's where we sell the most software. What you want to know is like what's the most surprising, what's the most informative. And so that's really the problem, this attribution problem, is something that we really dug into with Explained Data and built out that capability. Because we're focused on augmenting the human rather than automating processes. We want to help people explore and understand. And an important thing to realize about Explained Data is it's not trying to replace a human expert. It's really trying to help that expert explore more rigorously, find more things, maybe move more quickly, but you should not expect Explained Data to give you the answer or to tell you like the final conclusion, never mind tell you what to do about it. And so sometimes in marketing copy, I find myself having to sort of encourage people to be more precise with their wording, because we'll accidentally say things like, Explained Data will tell you why something happened. And it doesn't. It'll give you candidate explanations, but the notion of why is a pretty sophisticated statement about the universe, and your data almost never has enough information to really make a conclusion about why. So it's almost always the role of the domain expert, the user, to conclude that whatever the machine's showing them, that's really the why of what happened. You know, sales are down. They're mostly down in financial services. They're down, surprisingly, they're down in the Northeast. You know, they're down in Bob's territory. In fact, Bob's territory looks like a mess. You show that to a human expert, and they would be like, oh, well, I mean, Bob's on paternity leave. Joe's covering his territory, but it turns out Joe doesn't have permission to update Salesforce with the data. So it's not that anything's really wrong, it's that nobody's touched the Salesforce records in 6 weeks. The why underneath that is a pretty complicated why. And that's the exception, that's the rule, that's the most common case in business analytics, is that the whys are nuanced and complicated and not entirely described by the data. So let's jump into a quick demonstration. I'm sure everybody's seen an Explained Data demonstration at this point. Yes? Yeah? I make people raise hands. It's like a thing I do. You came to this talk without having seen it? Yeah, okay. Everybody's seen an Explained Data demonstration. All right. I hide down here, pull this up. So unfortunately, even though you all raised your hands, I'm going to give you a demonstration anyway, because I'd like to make sure that you've got this particular data set somewhat in mind for some of the things that go on further on in the talk. So here I have a data set. It's bike share data from Boston. If you've been to one of my other talks, you may have seen this data set before. This is, you know, it turns out the Blue Bikes program in Boston had a relaxed attitude towards privacy, in my opinion, but it means that you can get record level data on every ride that everybody took for the course of all of 2017. And so I have data like how long, how much distance that the ride went for. I have data like what month, you know, the ride occurred in, and I can very easily build a visualization in Tableau. And Explained Data is going to work off of any visualization that's been created within Tableau. And when I click that, what the system's going to do is fit a model to the data that's on the screen, and then surface a number of candidate explanations, fit models to those explanations, and then score and prioritize those explanations and decide what to show you. And so in this case, you know, what's different about August? Well, I mean, it is August, but in particular, there were a lot more overcast days in August than there are in general in the Boston area. And so in situations where there are more, people tend to ride their bicycles for longer distances on overcast days. And so that becomes a visualization that we can interactively add to things, or I can go and explain a different month. And because we're context sensitive, when I ask to explain, say, February, well, I mean, it is the winter, but actually the biggest difference in February is a difference in which city or which geography people are renting bikes in. That they are renting bikes almost exclusively in Cambridge in February. And that becomes interesting, and it's one thing that's very important about Explained Data is that it's embedded within the Tableau environment. So I don't just, you know, I can obviously bring this visualization out, but I could also just decide, you know what, I want to build a different visualization. I want to look at the that distance by city, and then I want to maybe show that by month. And actually, I know how to use Tableau a little bit better than that, and maybe I want to colorize something. And so then I can start to see that there's really a big difference in how these things vary over time. It's relatively flat in Cambridge versus much more of a summertime spike in Boston. Can anybody, even people who've seen this demo before, can anybody tell me why you might have a flat thing in Cambridge? You can just like sort of shout it out. Why you're more flat in Cambridge and more of a spike in Boston? MIT and Harvard. So Cambridge is student dominated. There's more students, and students have a more stable ridership. And conversely, Boston has a spike in the summer because it's actually much more of a tourist destination, and tourists like to do these bike share sort of thing. So that's interesting. If you actually take this to a domain expert, and frankly, we've been doing demos with the data for like a year before we did. If you take this to a domain expert, it turns out they actually take the bikes out of the rental stations in Boston in February. They're just like not there because they're like repairing or something. And so they were literally zero. And so in some ways it's explained by these sort of weather and human behaviors. And in other ways, there's this underlying factor in the data generating process that's sort of invisible unless you start talking to people who know what's going on. And that's important. Not always, the data isn't always going to tell you sort of why something is happening. There may also be cases where, let's say I'm here, I'm looking at all the stations in Boston. I can zoom in on this really, this is the average time rented. And Prudential Center shows up as the largest component of that. And if I go ahead and explain that one, then what I'm going to get is there's a single extreme value. There's one person who rented a bicycle for 460 hours, whereas in general, people rent them for about an hour and a half. And so this is an outlier, and it may in fact be just bad data. It's not. You need to know what you're trying to do in order to know what to do about it. But one thing I can do here is, if I have that extreme value, then you can see that Prudential Center really sticks out. Whereas if I take the extreme value out, and this, by the way, looks way cooler if you turn on that animation thing that you saw in Devs on Stage. If I take Prudential Center out, then okay, now it's the MIT, Harvard, Boston University become the largest stations. And so it really is, there's different things that could be going on. Sometimes your data is explicitly telling you what's happening. Sometimes there's something subtle behind your data that where your data reflects the real world, but maybe you need to talk to somebody to understand it. And in other situations, you may just have bad data, and you need to clean up the bad data in order to get to good answers. And so, how explained data works at like a super high salesperson type level is we start out taking the visualization that's in front of you, the data that's behind that visualization, what's on the screen, and to some extent how it's on the screen. And then we create a model for that data, and then we use that model to decide how surprising what you're looking at is. So in fact, if you look at the sort of top line within the explanations dialog, the first thing we tell you is that sort of expected range. And that's based on that first model that we fit. Then we go ahead and create explanation candidates. Most explanation candidates, and Rachel will go into more on this, most explanation candidates are additional information you could consider. And then we build models with that additional data. And what we ask ourselves is, does the point that you selected, does the market that you selected become less surprising given this additional information, when I model with this additional information? And that's what we're looking for, situations where the mark becomes less surprising. But even more than that, we're looking for good explanations. You can explain anything by just giving you the entire data table, as a spreadsheet, and say, why is the answer 412? Well, here's all the numbers. I got the math right. But that's not an explanation. An explanation wants to be simpler than all the data. And what we do is actually a trade-off between the complexity of the explanation and how much of the variance or how much of the surprise is explained by it. And so we're going to look for simple explanations or parsimonious explanations. So we'll allow an explanation to be more complex if it explains a greater fraction of what's going on. And then that's how we're going to choose to rank things. So that's my very pleasant way of describing this in various sales situations, and I enjoy doing that, but I actually have no idea how the rest of it works. And that's why I have Rachel Kelmar, who's a neuroscience PhD from Stanford and part of the Empirical team, is now the lead product manager for this. She's been a professional data scientist at several startups, as well as a fellow at the Harvard Berkman Center. And so I'm going to leave you in her capable hands to understand what's going on under the hood.
Great, thank you, Richard. So you have a little bit of a sense of where explained data came from and what it's doing. Now I'm going to crack open the hood and show you how the engine works. So the first thing that you're going to do, as Richard showed you, you're going to select a mark to explain. So going back to this bike share example, let's say we want to know, why did people ride so much in August? So we're going to select that mark. And the next thing we're going to do is we're going to model the visualized data, and we're going to calculate expected values and how unlikely this mark is. So here's my cartoon version of this viz that I showed you before, and the mark that we want to explain is August. So the first thing we're going to do is we're going to look at the data that falls between the 15th and the 85th percentile. And the reason we're doing that is because we don't want to make any assumptions about whether your data is Gaussian or not. So we say anything that falls between this 15th and 85th percentile, that's in the expected value range. So this is very simple, but we then say, okay, if you're outside of this range, then there may be something else going on that we want to look into. So we can look at this by drawing confidence intervals for each mark, and you'll notice that each of these are the same for every mark, and that's because we don't have any additional information in this viz. And so we represent this in the user interface by this line at the top. Under sum of trip distance, we say that the value of this mark is either higher, lower, or as expected. Then if you hover over it, we'll tell you what the expected range is as well. So this is our unconditional model. We don't have any other information other than what's in the viz right now. Then we want to ask, does the value of this mark become less surprising if we know something else about the data? So we're calling that our conditional model, and I'll go into more depth about this in a few minutes. So let's say that we know the weather. Suddenly, January, which is outside of our range of expected values for our unconditional model, if we know that it's cold, it's now no longer surprising that people didn't bike as far. So as I mentioned, I'm going to come back to this, but I just wanted to figure out how to use a pointer. All right, so I just wanted to walk you through our general approach that we're going to use across different explanation types. So the first thing we're going to do is we're going to figure out an unconditional score. So in this case, we're looking at a z-score, if you're familiar with that. And so we are going to compute the z-score of the mark with only the visualized dimensions. Then we're going to add in more data or model the mark in some other way, and we'll compute a z-score under the conditional model. And then we're going to compare the scores, and we're going to say, does knowing more information about this mark let us have a less surprising view of this mark? And so if the conditional score is better, then we'll consider this explanation as a candidate. And I just want to say up front that how we compare different scores, that's outside of the scope of this talk, so I'm not going to talk about that today. Okay, so now we've selected our mark to explain, we've modeled the visualized data, we figured out how to get PowerPoint to work again, and now we're going to create and evaluate models for different types of explanations. So before I talk through the different explanation types, I want you to know that as somebody using explained data, you don't need to know that there are different types of explanations. You can click on the light bulb icon and you can look at explanations, and it's not important to know what type it is in order to be able to use it. But if you want to understand how the different types of explanations work, we need to, we're doing that differently for different types of explanations, and so we need to tell you about each one separately. So the first type of explanation is an extreme value explanation. And so this is when the aggregated value of a mark is an outlier in the visualized dimension. And so in the example that Richard showed you, where the total time that people rented bikes from Prudential Center was way higher than from other stations, this is an example of an extreme value. So what we're going to do is we're going to turn this into a cartoon again, and then we're going to say, okay, for our aggregated mark, let's look at all of the rows that make up this mark, and let's look at the time rented for each ride, or for each row. And as we saw before, there was one very long ride. And so if we remove this very long ride, our question is, no. Great. Again, we've removed the extreme value, and now we can ask, is the value of this mark less surprising if we take away the extreme value? And so this is for a sum, but this works also for averages. And so basically what we're going to do is we're going to say, if your mark is an outlier in a visualized dimension, let's try taking away the most extreme values. Let's try taking away the maximum value. Let's try taking away the minimum value. And if the aggregated value of the mark is less surprising once you've taken away that value, then we consider this a candidate explanation. And so for our Prudential Center example, taking away this very long ride made this mark less surprising. So the next explanation type is noise. So what we're trying to do for this type of explanation, but for all of the explanations, is to try to model the underlying true value of each mark. Now, we consider a mark surprising if its true value is different than other marks. Now, if we don't have very many rows or very many rows for this mark, then it's going to be difficult to get a good estimate of the true value. There's going to be a lot of uncertainty there. And so if a mark looks extreme, but it doesn't have very many rows, then it could be that the reason it looks extreme is just due to random variation or statistical noise. And so in the bike share data set, the watermark Seaport station looks like it has a very low average trip distance from trips taken from this station. But there were only 3 rides taken from here. So this wouldn't be surprising at all if somebody came along and took a ride that was 1 mile. However, if there had been 3,000 rides from the Seaport station, and then somebody came along, and they were all short, and then somebody came along and took a longer ride, this would be more surprising. And so here we're looking at the number of rows, and basically if something looks extreme, but it doesn't have very many rows, then we say, you know, the reason it looks different may just be due to random variation. And this is the kind of thing that trips up business analysts all the time. Their data looks like it's really an outlier, but often it's just noise because there's not enough data to be able to say that. So the next type of explanation is number of records or average value. And so again, we're going to look at our example where people rode bikes more in August. And so we want to ask, is the reason why people rode bikes more in August because people took more rides, or because the average distance of each ride is longer? And so this type of explanation only works for sums. And so basically, we can look at each sum as the number of records times the average value of each record. So we're going to break apart this distribution to two new distributions. We're going to look at number of rides, and we're going to look at average distance per ride. And so if a mark is an outlier in the for total distance, then it's either going to be an outlier for number of rides or for average distance per ride or for both. And surfacing that is going to allow us to ask the next question, like, well, why did people take so many rides in August? Before I get to the next explanation type, I want to give a disclaimer that explained data is a feature that we're actively working on. And so some of the explanation types are things that we might be changing over the next sets of releases. And so I'm going to describe the next type of explanation, but keep in mind that even though it's what we're doing now, it may not be what we're doing even a week from now. So the final explanation type is unvisualized dimension. And there are three subtypes of unvisualized dimensions that I'm going to talk about. There's also another explanation type that's new in 19.4 called unvisualized measures. I'm not going to talk about those today, but you can think of them as similar to unvisualized dimensions, but for measures. So what we're doing for all of the unvisualized dimension explanations is asking, can we model this mark better by looking at properties of an unvisualized column? So the first type of unvisualized dimension explanation are disaggregated dimensions. So here we're saying January, one potential explanation for why distance traveled in January is low is because there were more cold days in January. So here's our cartoon version of this. So I've disaggregated each of these marks and broken it down into the distance traveled for cold rides and the distance traveled for warm rides in green. And so the question is, if we model this mark by modeling each of these submarks separately and then adding them together, do we do better? So we want to ask, what's less surprising? The distance traveled in January without knowing anything about temperature, or the distance traveled in January, or prediction of the distance traveled in January if we knew that it was cold, and the distance traveled in January if we knew it was warm, and then adding those together. So if it's less surprising, if the value of this mark is less surprising by modeling it that way, then we consider this as a candidate explanation. The next type of explanation is aggregated dimensions. And like the previous type, we're also going to be looking at the submarks for cold and warm rides. But here, rather than looking at the row level detail, we're splitting apart, or we're looking at this mark as a ratio of cold days to warm days. And so we can represent this by looking at the percent number of rides when it was cold versus when it was warm. So the blue here is for the selected mark, so we're looking at January. And the white is all marks. And you can see that in January, more of the rides happened when it was cold. Also, we can look at the average trip distance for cold days, or for cold rides versus warm rides. And we see that cold rides tend to be shorter. And so here what we're saying is January had more cold rides tend to be shorter, and so this is a possible explanation. We can also represent this as a scatter plot where we look at total distance as a function of the percentage of warm days. And so we can plot each mark here and run a regression to give us a prediction of what we expect the distance to be if we know the ratio of these subtypes. And so if our prediction is less surprising than our original mark, then we consider this a candidate explanation. Now, the final type of unvisualized dimensions are total variation distance explanations, or TVD. And so here what we're asking is the distribution of submarks for this mark different than the distribution overall? So in August, we saw that there were more cloudy days. You can kind of see that here. We're going to break this out into a new viz, and we're going to look at, again, blue is the selected mark, and so we see that there are more of the rides happen on cloudy days in August than in rides overall, or in months overall. And so what TVD is, TVD is a measure that allows us to assess the similarity of statistical distributions. And so what we're looking at here is that we're saying, is August different or distinctive from the distribution of weather conditions across the rest of the year, and is it also different than other months? And if it is, then we consider this a candidate explanation. Now, there are two caveats to this type of explanation. For all the other types of explanations, I was trying to explain why August was high. But here, I'm not saying anything about about the value of August. I'm just saying that August is different than the other months because it has a different distribution of across this other dimension. And so the second caveat is that this is where you really need to bring your domain knowledge to the table. So if I were looking at, say, percent of snowy days, or trying to explain percent of snowy days in January, and I got an explanation that was about new subscribers. You know, new subscribers don't really have anything to do with snow, but they both happen to exist in January because January is winter, at least in Boston, and so we have snow, and January is also a typical time of year where you might have new subscribers, but those don't really explain each other at all. And so with this type of explanation, but with really all of our explanations, you should consider these explanations not as answers, but as starting points. But it's really important for you as the domain expert or somebody with domain knowledge to ask, does this make sense? So just to summarize, the different explanation types that I talked about were extreme value, so extreme value explanations. There's a single row at the record level of detail that's skewing the aggregate value of the mark. Noise explanations, where you have a small number of rows, and so even if something looks different, it may just be due to statistical noise. Number of records or average value, where the number of records or the average value of the target column is significantly different than the others. And unvisualized dimensions or unvisualized measures, where the mark's value can be partially explained by the mark having a different distribution or aggregated mix of values that's not present in your visualization. So we've selected a mark to explain, we've modeled the visualized data, we've created and evaluated models for different explanation types, and now we have a list of candidate explanations. The next thing that we're going to do is to filter and rank those and then display them. So we end up with a long list of candidate explanations, and we put the simpler and more informative and more certain explanations at the top of this list, and the more complex, less informative, and less certain explanations at the bottom. We have a threshold for informativeness, where if things don't cross this threshold, then they're not included on this list. As I mentioned, how we do that is beyond the scope of this talk today. So we end up with a list. We've taken away the least informative and the least certain explanations, and we surface them in this list here. And then, as we showed you before, we present each explanation with a natural language string and with a viz. So when you click the light bulb, these are the steps that we go through to surface explanations. Now, with a little bit better of a sense of what we're doing behind the scenes, it's also important to keep in mind some ways that you can get the most out of explained data. Now, the best thing to do would be to go see this talk on leveraging explained data. Unfortunately, it happened yesterday, so unless you happen to have access to time travel technology, you won't be able to go in person, but it should be online, so I recommend making a note of it and looking it up and checking out the recording. I will leave you with a few best practices for data preparation, though. So one thing that you're going to want to do is to give your columns good names so that when you surface the columns and explanations, you can make sense of them. Obviously, since we're using unvisualized columns in our explanations, you don't want to discard columns that you're not visualizing. low cardinality dimensions are going to work better. Since we're looking at row-level detail for our explanations, you don't want to pre-aggregate your data, unless, of course, your data is really massive, and then you'll want to pre-aggregate to an appropriate level of detail. And finally, you're going to want to eliminate redundant columns and data prep artifacts so that those don't surface as explanations. So these are some things that you can do that will help you have a better experience with explained data. It's also useful to keep a couple things in mind about what explained data is and what explained data is not. So explained data is not a statistical testing tool. It's not a tool to help you prove or disprove hypotheses. Explained data is not telling you anything about causality either. What we are doing is we're giving you a way to leverage your domain expertise. We're giving you a tool that recommends where to look next and that surfaces relationships in your data. And this is also a way to expedite data analysis and to make it more accessible to a broader range of users. And as I mentioned, we are actively building and developing and iterating on explained data, especially trying to make this accessible to a broader range of people. And so we are interested in hearing from you about what would be useful, where you're using explained data now, where it's working well, where it's not, what kinds of things your dashboard users might be interested in seeing. We are always running ongoing user studies, and we'll have alpha and beta versions of our next releases. So if you're interested in getting involved in any way, we'd love for you to send us an email. Feel free to email Richard or myself. We also have a short survey where you can indicate where you've tried to use data or what your interest is at this link, and this is a case-sensitive link. And with that, I'm going to leave you with the reminder to complete the session survey, and I'll open it up to questions. Thanks.